let's set up the following. Okay, in the previous exercise, they did a calorimetry experiment where they told us about calculating the heat transacted per mole of a substance. You know, that's a pretty useful concept because think about it. We talk about molar masses like the grams per mole. We talked about that in the past, right? Or, for example, the liters per mole of a gas. So this per mole thing is very useful. So let's do this. We're going to do something that physical chemists like to do. They invent properties. We're going to invent a property. We're going to call it enthalpy. We're going to give it the symbol capital H. And we're going to say that H is the sum of the total energy, the internal energy of the system, plus the pressure times volume product. And you're going to ask, where did that come from? What does that mean? Hey guys, right now it doesn't mean anything. Like I said, it's an invented property, okay? From our perspective. Now, if you ever take a physical chemistry course, you'll see where these ideas come from, but don't worry about it for now. Simply stated, H, the property of enthalpy that we just invented, is a state function. In other words, a change in enthalpy, delta H, can be written as final minus initial, right? Final minus initial, just like we did before with temperature. Final temperature minus initial temperature. Now here's the catch. In our world of chemistry, we have just said the system that I'm interested in is a chemical reaction. What is the initial and the final state in a chemical reaction? Well, the initial state is the reactants, and the final state is the products. So what I'm trying to find out is there a way that I can calculate this as some kind of an energy function? Notice that it is based on energy and work. So is there a way that I can measure this delta H? Because that tells me some kind of energy change that's happening in going from reactants to products, all right? And let me show you how we are going to set this up. Let's consider a system at constant pressure. This is what we call an isobaric process. Isobaric process, all right? So let's say, for example, I have something happening inside a container there on the left, bottom left, and there's an expansion of gas against a constant pressure, P. And as a result, there is a change in volume, delta V. Okay, let's go back to our thermodynamics. First law. The change in energy of my system is Q plus W. I'm going to put a subscript of P under the Q just to remind me that this is happening at constant pressure. And of course, work at constant pressure is minus P delta V. I'm going to take that reaction and that equation, and I'm going to rearrange it. All right, I'm going to rearrange this equation. I'm going to say QP equals delta E plus P delta V. Okay, hold on to that for a moment. Okay, don't do anything with it. Remember we said I'm going to make this property enthalpy, and I'm going to say that it is E plus PV. So if I have a change in my system, there's going to be a delta H, which would be delta E plus delta PV. In other words, the change on the left is the change on the right. And since it's a sum, we can simply kind of like rearrange it or arrange it so it's delta E plus delta PV. But remember, in the pressure times volume product, the only thing that's changing is the volume. The pressure is staying the same. So I can factor it out, and I can write this as delta E plus P delta V. See that there? Where did we see that before? Oh, wait a minute. It's right up here. What is delta E plus P delta V? Well, it's actually the heat that was exchanged in this reaction. In other words, if I carry a chemical reaction at constant pressure, the energy that is transacted, or the heat that is transacted in there, is now a change in a state function. There is a final minus initial. Now, the idea is I'm going to measure the heat, but that is going to be converted into something that is actually a function of state. All right, so let's go to the next slide and say this enthalpy change delta H of a reaction is the heat evolved in the reaction at constant pressure. Like we just saw, delta H equals the heat of the reaction at constant pressure. And because of that, we use the nickname or the phrase that this is called the heat of reaction. Now, we still have a problem because we've talked about delta E and we've talked about heat, and we saw that there's some reactions you can measure the heat for using a bomb calorimeter, not all of them. But the problem is this delta H, it's still kind of a bit of a mystery because we invented that property. So what we're going to see is we're going to do a little exercise here in a few moments. And we're going to practice doing this by saying that essentially in most chemical reactions, delta H and delta E are pretty much going to be the same. In other words, for practical purposes, the amount of energy exchange that happens in a chemical reaction at constant pressure is due to exchange of thermal energy. It's pretty much all heat. All right. So let's go ahead and look at this following exercise, and I'm going to try to convince you of that. Okay. Here is a chemical reaction that represents what happens when you put sodium metal into water. There's the picture on the left. That's what happens. I would not do this in classroom with you because you could get an explosion in here. You could get fire and stuff. The products are NaOH and hydrogen gas. And as you can see from the top there, this is a reaction that generates a lot of energy. Okay, so let's go back here. I'm going to go back here to our doc cam. Okay, we'll be done in a few moments. Let me pull this over here. So here's our chemical reaction. Okay, let me put us back in there. Yep, there we go. Okay, again, make sure you pin this screen in your Zoom. All right, so let's consider what we just talked about. Let's say delta E equals to, we said the Q minus P delta V. And we said that in a reaction at constant pressure, the heat is actually this function called the enthalpy. Now, let's consider 1 mole of gas. Let's say that we have a reaction where we produce 1 mole of gas. And let's say that we're going to do this for the sake of illustration at 25 degrees Celsius. Now, you guys did an experiment. Well, you didn't do an experiment. You followed along a virtual experiment just now, experiment 5, and you're calculating things like what is the liters per mole of a gas under our lab conditions. Well, it turns out that for 1 mole of gas at 25 degrees, this comes up to about 24.5 liters per mole. All right. And, some of you in your calculations of the mock data that you received might have gotten something kind of in that range there. It might have been smaller, but less, doesn't matter. So let's say, therefore, of course, This would be, I'm sorry, at 1 atmosphere. So I'm going to give you that, okay? This is just a given. It's not like there's no magic in it. I'm just giving you this value here, all right? So let's consider what is a P delta V for this process. Again, notice that we start out with the system inside a piston, a container with a piston. I add the sodium, and then when it starts reacting, the hydrogen gas is produced and it pushes against that constant pressure. And let's say that we have a situation where there's 1 mole of this gas. So what would be P delta V? Well, it would be 1 atmosphere of pressure. And delta V would be, well, this would be from 0, or let's see, from V initial to V final. And we're going to say that the difference between those was 24.5, because that's what we're saying. We produced 1 mole. So this would be 24.5 liters. And in order to get units of energy, we had to convert that to joules. So I gave you that conversion, I think, in our previous lecture. That would be 101.3 joules per mole. I'm sorry, not per mole, sorry, per liter per atmosphere. Sorry about that. And to be able to compare with the other value we have, I'm going to convert that to kilojoules. So remember that 1 kilojoule is 1,000 joules. Okay, so liters and liters cancel out, atmospheres and atmospheres cancel out, joules and joules cancel out, and this ends up being essentially, let's see what it is, 24.5 times 101.3 divided by 1,000. So that's about 2.48. So let's put that in here. 2.48 kilojoules. Let's see what the energy change was total. So delta E was delta H minus P delta V. Okay, the energy, the delta H is over here, minus 367.5 minus 2.48. So let's put our calculator back here. 367.5 minus 2.48 equals this, 365.02. Again, you have only 1 decimal here, so let's 365. Kilojoules. So you look at this and you realize, okay, this is a chemical reaction that released 1 mole of hydrogen. It occupied 24.5 liters of space. That's how much it expanded. And in the process, the total energy was only different from the enthalpy by a couple of kilojoules. Remember, most chemical reactions, for example, acid-base reaction, redox reactions, most reactions don't even release a gas. Most reactions have a change in volume that's near 0. All right. So in other words, when we're studying chemical reactions, for all practical purposes, the only energy exchange that is, meaningful, significant, measurable by us is essentially the heat of the reaction. Okay? Now, if you are thinking about, a reaction that generates, liters and liters and liters of gas at a certain pressure, of course, there are scenarios where you'll consider that. Most of the chemical reactions that we'll talk about are not going to proceed with a considerable change in volume, and therefore the majority of the energy exchange that will happen will be in the form of heat. Hello, this portion here is a few seconds after we closed our session. Several students pointed out that I had made a couple of mistakes here. So here we go. Let me take you guys here to our actual page. So when I did the first calculation, I guess I had forgotten about the signs, and for some reason I ended up saying it's 365. But I have forgotten it's actually minus and minus. So it should have been about minus 370. And then on top of it all, I forgot to put the negative sign over here. So this here is the final page. This is what I'm going to be scanning and posting to accompany the recording, okay? Again, I apologize for that, and I hope you'll be forgiving with me. And I will see you later. Thank you. This. So since this delta H change at constant pressure is essentially the heat of the process, just like we did before with heat, we can say that a delta H negative represents heat being released by the system. In other words, an exothermic reaction. And when delta H is positive, heat is being absorbed by the system. So this is called an endothermic reaction. So notice that what we've done is by doing a chemical reaction at constant pressure, we have turned the heat of the reaction into a property that is essentially a state function. All right. So let's go on to the next one here. Once more, like before, this is the same diagram as before, system and surroundings. If heat is released, that's an exothermic process. Delta H is negative. If heat is absorbed by the system, that's an endothermic process. Delta H is positive. So it's the same thing as we did before, except that we're now, instead of using just simply Q, right, we are talking about a property that's a property of state. And of course, don't forget that in this particular scenario, when we say the system, we mean the chemical reaction itself, right? That whole bunch of molecules that are doing things to each other in that container, all right? So what we can do is we can go back to our energy diagrams that we did before. I hope you remember these. For example, let's look at the process of the melting of ice. The melting of ice, if we measure the enthalpy change, the H change, we find that as ice melts, it basically absorbs heat from the surroundings to the sound of a delta H of 6.01 kilojoules per mole. So it's delta H negative or positive. Okay, well, we know from experience, right? The ice is absorbing heat, so it's endothermic. Therefore, delta H would have a positive value. So the statement I'm making is that 6.01 kilojoules are absorbed for every 1 mole of ice that melts. And of course, we had to specify the conditions. Of course, we know that ice melts at 0 degrees Celsius and 1 atmosphere pressure. Now, what I can do then is I can write the equation for this process, and although this is not a chemical reaction, right, this is a physical change, we will write H2O solid converts to H2O liquid. And what we did was, on the right side, we added an extra piece of information, the delta H for this process, the heat of this process. And this combination of the chemical equation with the value of delta H is what we call a thermochemical equation. Now, what I show you here is actually a physical process, it's not a chemical change. Let's look at an actual chemical reaction. Okay, here we have the combustion of methane, CH4. And you can see the reactants have a higher value of enthalpy than the products. And it says that in the process, delta H is 890.4 kilojoules per mole. Remember, we saw that table earlier on. So again, if we follow along here, is delta H negative or positive? Well, the system is giving off heat. We know that from experience because when you burn, when you light up a Bunsen burner, it gives heat. This is therefore an exothermic process, which means that it has a negative delta H. That's our Bunsen burner burning there. And again, what we're saying is that for every mole of methane that is combusted at 25 degrees in 1 atmosphere, 890.4 kilojoules are released. So what I'm going to do is I'm going to write this chemical equation here, CH4 plus 2O2, producing CO2 and water. And what I'm doing is, I've already seen that reaction before. I have balanced that equation in class. And what we find is this extra piece of information here, that there's a delta H of minus 890.4 kilojoules. So this is what we call a thermochemical equation. It has the equation itself fully balanced, and then to the right, it has the value of delta H. By tonight, I will have this recording posted on Canvas, as well as scans of the pages here, of course, with the correction that we just made here. See, Dr. D is not perfect. Sorry about that. But anyway, hey, thanks for joining. I hope this was helpful to you. And don't forget to follow up on the assignments that are due. If you have any questions, don't hesitate to contact me by text or by email or by Canvas. Just, be patient with me. Sometimes I can get to them right away. So I'll try my best, okay? And there's other things that I'm going to be doing. Please look at your announcements and emails so that you can be on top of things. Okay, guys? Great being with you. And I'll see you on Wednesday, and I'll send the information for that link later on. Thank you.